So we're going to talk about interrupts. Interrupts can happen in the hardware sense and in the software sense. So basically, you know, definition of an interrupt, you've heard the word interrupt. Or what would you say is the definition of to interrupt something?
Well, the interrupts are good for processors because it lets multi-functions go through.
Okay. But I'm just saying, okay, so in just the dictionary would be to stop continuous progress, right? And then from a hardware point of view, it would be, you know, they're used by devices to communicate that there's a problem. And there's also software interrupts. And an interrupt while software is running, an event occurs that is going to stop the normal processing of a, of a program that's running. So for example, now one thing we could do is we could use polling. So in other words, like let's say right now, let's say I'm teaching a class and I'm going over, you know, the dictionary definition of interrupt. Now one thing I could do is after I cover that, I could ask all the students, are you okay? Do you have to go to the bathroom? Do you need a drink? And you know, I could like check with you, I could take a poll. Does anyone need to interrupt me for anything?
Yeah.
And if nobody needs to interrupt me, then I go over to the next topic and then I take another poll. Do you need to, you know, do you need to interrupt me now? So that could take a lot of time. So one thing is polling, where every once in a while, maybe we have a process running on the computer that checks to see if anything is causing an interrupt to happen. We'll get into what kind of interrupts in a second. But another way to do it would be if I could just, like as a teacher, I could just keep teaching, and then if you need to interrupt me, you just yell out, hey, hold on, I got a question, or I got to go to the bathroom, or something like that. So I would just keep processing like normal, and then if something unexpected happens, you just yell it out. So that could save a lot more time than using polling.
Would a hardware interrupt include basically like a computer overheating and then
Right. So
saying,
an interrupt is basically like the computer's running and it's expecting to, you know,
perform functions.
Yeah, perform with no problem. But so let's say, for example, a computer overheating. Let's say the fan breaks.
Yeah.
And then it starts getting too hot, and it has a temperature that says once it hits this temperature, it's going to shut off. So it needs to alert the computer user.
Yeah.
Something unexpected has happened, and you need to answer to it. Well, like if you're printing let's say you're printing a 10-page document, and the printer only has 8 pages.
Paper jam or
paper,
ink.
So something unexpected happens, it needs to send a message saying, okay, normal processing has to stop, something went wrong. Okay, so just, you know, we've talked about it, we've used this picture earlier in the course, and we've basically said that the way a normal program is running, we have, your code is in this, what we call the control store. So all your assembled code, your 32-bit instructions are all listed in here. And we take an instruction out, and we put it on the processor, we put it across these 32 bits. We let the wires turn into zeros and ones. That turns on and off pieces of the computer's architecture. And after 4 clock cycles, the instruction has completed. Whatever it's trying to do, add 2 numbers together and put the result somewhere, has been completed. Now we have to go and get the next instruction. So we take this register has the address of the current instruction. We feed it through an incrementer, which adds 1 to it. And then we use that as an index into our control store, and we get the next instruction to come out. So we increment the program counter by 1, and then feed that into the program, where all the 32-bit instructions are, and we load the next instruction, and then let that one run. So the processor just keeps running instructions over and over and over. But what if an interrupt comes, something, you know, the printer's out of paper or something, and we feel we have to stop your program immediately and start up some other program. So like I was saying with polling is, when the operating system is allowing 10 programs to run and time share the processor, it could allow an 11th program in that just polls all the hardware to say, do you have any problems? And if they all answer no, we go back to what we used to do. But what we can do instead is just let the processor run as if there's no problem. And then if any problem shows up, we need a way electronically to say, instead of going to the next instruction, we're going to have software that handles the interrupt. So like, yeah, maybe a window pops up on the screen that says you are out of printer paper, do you okay.
Yeah.
Sometimes it just tells what the problem is and there's an okay
Yeah,
button.
yeah.
All you can do is hit okay.
Okay.
But at least it's letting you know that's happening. But that's some software. Some
Yeah.
software had to run. So what we'd like to do is have the processor run the way it normally does, and then just somehow say, okay, wait, a piece of hardware has reported a problem, and we're now going to jump to some other program, and maybe when it's done, we can then jump back to where we were before. So that would save on polling. So it might be a good idea for us to introduce a new register. And so the new register, we could call it the interrupt register. This is one, there's no perfect way to do this, but we can add a new register called the interrupt register. And let's say the interrupt register is 32 bits or 64 bits. And so in this case, I'm just going to use a nibble. I'm just going to use 4 bits to keep it simple. So we could say if the value of the register is all zeros, that means there's no problem. And then if it has any other value, the number in the register is the problem. So let's, this is a silly example, but let's say problem 1 is the printer's out of paper. And problem 2 in binary is the processor is overheated. And process 3 is the disk drive is disconnected. 4 means, the yellow internet cable was pulled out of the wall. So in other words, some piece of hardware wants to communicate to the operating system that there's a problem. But we don't want to poll them because that would take too much time. So we have them all just write a number into a register. And each one is assigned its own number. So now, and the reason we want to do this is so we don't have to poll and we can very, very quickly realize there's a problem. So if we had a 4-bit register, and all the values were zeros, we could OR all the bits together, and this would obviously work if it was 32 bits or 64 bits. We could OR all the numbers together, OR them together, and this output would be, what would make this output become a 0? What would the value in all these register bits have to be for this to come out as 0? All zeros.
Yeah.
So if they're all zeros, this wire will be off, and if this wire's off, that means there's no problem. If there's any problem, if some piece of hardware writes their number, so number 4, what did we say that was? Number 4 was the internet has lost connection. So the part of the computer that has the yellow wire coming in, the Ethernet connection, if it disconnects from the wall, it'll write a number 4 into the interrupt register, which allows us to know, well, this wire is going to turn on just to say there's a problem. And then when we go to figure out what the problem, we have to say, all right, now how do we handle problem number 4? But in the meantime, at this point, the interrupt register is not a 0, which turns this wire on. If it contains a 0, this wire would be off. So this is a wire that will just turn on whenever there's a problem. So then what we can do, we just kind of expand the picture a little bit more. If the internet disconnects and we write a 4 into this area, one wire, we just say this is the wire that says there's some problem. Then what we can do is, out of all the possible problems we have, if we want to solve problems using hardware interrupts, we then take these bits and compare them against the number 4. So remember earlier in the course we had a comparator where we take like 4 bits and have another 4 bits and a wire would turn on if they matched exactly. So this is going to take the 4 inputs and compare them to the numbers 0, 1, 0, 0, and turn this wire on if there is an exact match. And if this wire turns on, these feed these AND gates, then we could put in another register the address of the first instruction of the code that handles problem number 4. And if problem number 4 is, the internet is disconnected, that might be just code that puts up a message and says you are no longer connected to the internet, go figure it out yourself, and put an OK button. And then, so I guess what I could have drawn this, but I didn't want to make the picture too clumsy, was this comparator and this starting address, there would be one of these for every problem every hardware problem the computer could have. And then every one gets run into these OR gates. So eventually, if we put the number 4 in here, electronically this wire will turn on and the address of the first instruction of the code that handles that problem would get written into this register. So we kind of have one register telling us that there is an interrupt and which one it is. That would then translate electronically very quickly to say, here's the address of the first instruction of the handler for that. So what we want to add to this picture is, I don't know if you remember when we talked about this picture at the beginning of the course. We're running an instruction in a normal program that doesn't have any interrupts happening. And when you run an instruction, where is the very next instruction that's going to be run? Well, usually it's the instruction right after the current one, usually, but not always, right? Remember, sometimes we would jump somewhere. If there was an if statement and we would jump into the then block, or maybe we had a while loop that when you hit the bottom of the loop, you then jump to the top of the loop again. So usually the instruction goes to the next instruction after the current one, but sometimes it jumps somewhere. So what we used to do is, and what we still do, is we would always calculate based on the current instruction. We'd always increment it by 1. So that was kind of like a nominee for what the next instruction is. And then also, there's a possibility that we would jump to some address. So we'd take this address. Now, out of the two choices, the next instruction or where we're jumping to, we would have this wire, this AMUX. This wire could, no, not this one. Where is it? Yeah, this AMUX wire would feed into, I'm sorry, the condition code, should we jump or should we not, would feed into this logic. And if the last result came out either was a zero or a negative number, may turn this wire on or off. And this wire being on or off determines whether we pick this address or this address as our next instruction. So now what we're going to do is probably put another mux between this and this that says, should I run the next instruction of your program, or should I run this instruction? Should I run the first instruction of the interrupt handler code? And what's going to determine that? If this wire turned on. So if that wire turned on, so basically we have another, so here's a mux that's taking 2 inputs and picking 1. And now we're going to, between here and here, we're going to have another mux. Should I take your program's next instruction, or should I take the interrupt handler's first instruction and start running that one? And then that's how we could run the interrupt handler. Now the thing is, if we wanted to, maybe after the interrupt handler is done, your program should be able to pick up where it left off. Right? You know, it might be, so the interrupt handler might be a message saying, you know, your printer's out of paper. You go put in some new paper and then your program should continue. We shouldn't kill your program. So maybe the first batch of code of the interrupt handler should be to save where your program left off. So then it handles the interrupt and then reloads the way where yours left off and pick up. So that'll be a nice courtesy if they did that. Okay. Okay. So really that's, from a hardware point of view, the idea of doing it this way, having a number put into this register and then just letting hardware immediately load the address of the next instruction and turn a wire on, which will determine whether we run the next instruction of your program or the first instruction of the interrupt handler. That could be solved instantly. As soon as you put a number here, bang, the next instruction to run will be the interrupt handler. So it's done very, very quickly. We could also do this in software. We could accomplish the same thing but doing it slower. Basically saying if any piece of hardware has an interrupt, it can write a number to a register, and we could even use polling. We could keep checking every once in a while, is there a number there? And then if so, a low priority program will then run and say, okay, now I'm going to handle the interrupt. When that's handled, you go back to all the other processes. So in software, it's usually slower, but more flexible. Right? As Bill Gates says, with software, you can do anything. Right? Hardware, you have limitations, but hardware is a lot faster than software. So one of the design things that came up with software problems, as opposed to hardware problems, is, well, physical hardware problems are going to affect hardware and software, right? So if you have a program that's printing out a 10-page document, there's only 8 pages in the printer. There's no way software can get around that. But sometimes there are problems that software will have that really isn't an issue with any hardware. So for example, suppose you wrote some code that opens up a file. And if the code that opens up a file, goes to open the file and the file is not there, because maybe somebody deleted the file, then that's not really a hardware problem. That's just your software expected a file to be in a certain location, and the file wasn't there. So now, with the file not there, the question is, should your program die, or should you be able to handle your program? You know, should your program be able to continue running if you know what to do in the event that the program, that the file not there? You have maybe a backup input file that you want to use. So the operating system, in a software point of view, where we have a little bit more flexibility, we can build a stack of all the possible interrupts that may impact your program. And then if a problem occurs, we capture the problem, and then we can just go looking down the stack until we find a problem that matches the one that has just occurred. And then your stack is basically a list of problems, like file not found, and divide by 0, and then interrupt number 28, which could mean you disconnected from the internet, and interrupt number 2 means the printer's out of paper or something like that. So when the operating system loads your program in, it can go and get all the possible interrupts that may impact your program, put them on a stack, you know, most likely to least likely, and then they could, the operating system can give your program the ability to add more possible issues that could come up during the processing of your program that could impact your program. So when a problem occurs, you can take what the stack the operating system gave you and add more possible problems that could come up. And if that problem comes up, you can supply the code that handles it. So here's your program, and these are programs supplied by the operating system. So maybe this is interrupt number 13. So interrupt number 13, maybe that's the internet has disconnected. If that problem occurs, here's some code that should run to handle that problem. And if problem number 2 occurs, somewhere over here is the code that handles that problem. And if problem number 28 occurs, we should go and handle that problem. Now all of a sudden, your program, you write a program, and your program is, you write the code of your program, and then within the code of your program, you can attach to it a way to handle file not found interrupts. So if your program is running and goes to open up a file and the file is not there, instead of having the hardware kick your program out, you could say, oh, I anticipated that problem occurring, and here's what I want to do about it. So you can write code within your program. So let's say your program here is opening up a file, reading the records in the file, making some decisions, sending out some emails, and then closing the file and ending. But you anticipate that every once in a while the file you're opening is not going to be present. So maybe like some program is delivering it in the middle of the night and your program runs the next day, but last night they didn't deliver it. So you could say, you could have code that says if the file is not there, no big deal, I don't want my program being killed. You could write code that says just print out, you could use yesterday's file, or you could say, yeah, I have no new information, but here's yesterday's data, you know. So maybe you don't want it to be such a big problem. And then maybe there's another problem that you hit from time to time. You're reading two numbers and you have to divide them, and once in a while you read in a zero. So maybe you have some code that handles that problem. So what you can do, like I was saying, when your program is loaded, the hardware stacks up all the possible hardware problems that could go wrong, and even some software problems that could go wrong, and the operating system supplies its interrupt handlers, code that handles those problems. But now in software, because software is a little more flexible, you can write code and then say, all right, I'm aware that from time to time I may hit these interrupts. We're going to come up with a new name for software interrupts in a second, and here's how I would like to handle them. If the interrupt never happens, this code would never run. But you're supplying this in your file. So programming languages like C++ and Java allow for this, to handle software interrupts. Okay. So they're typically called exceptions in software. When an unexpected event occurs during the processing of your software, so yeah, you take two numbers and you divide one by the other, and it turns out the denominator is 0. And normally that doesn't happen, so that was unexpected. You go to open up a file that's not there. You ask somebody for input, and then you have a timer runs, and they took too long to answer. So when unexpected events occur in software, we're not going to use a hardware interrupt register to throw a number in and have the code start running. What we'll do is, as soon as the event occurs, a message could be sent to say, a message could be sent to your program saying we've had this exception occur, and we need to handle it. So just to take a look at, an example where you could have a software exception. Okay. Software exceptions and hardware interrupts kind of mean the same concept. So you can have some code, and you run an open. You open up your file, input.txt, and you open up the file, and then your code is supposed to take this file, which now has successfully opened, and has to be there to be opened, and your program has to have the same permissions as the ownership of the program, otherwise it'll have an ownership problem. You read the file into a variable called s, or string, an array of strings called s. Then you call some routine you wrote called do stuff with it, and then close the file. And close usually means save it the way it is, so maybe you're changing the content of it. So this should work fine, but what if this file doesn't exist? Or what if it exists but you don't have permission? Your program doesn't have the same permissions. Someone changed the permissions on the file, so you can't open it. So now the question is, should the operating system say, file not found, and kick your program out? Or should you be able to write code and say, all right, normally that doesn't happen, but if it does, just do this, don't kick me out, to keep it more graceful. So what you can do is start putting interrupt handlers. You can write them in your own code and put them on top of the stack. So 3 kinds of exceptions are checked exceptions, which are ones that the user can anticipate, kind of like a file not found. If you writing code that opens files that may or may not exist when the program runs. Error exceptions are exceptions that are external to the application, like a hardware issue. So that would be like you're printing a document and the printer is unplugged or runs out of paper or something like that. And then runtime exceptions are ones that have logical errors in them.
Code exception, sure.
Yeah. Right. So, okay. So the way you can, so now this is not really going to be a programming class. So, so for example, I think this could be C++ or Java. No, C++, virtual. Right? The word virtual doesn't show up in Java programming language. All right, so in other words, we can even have a inheritance hierarchy for issues. So for example, we can have a math error. And then a math error could inherit, we can have an overflow error. That's where you take, like, let's say 2 32-bit numbers, You add them together and you get a 33-bit result, but you can't fit the result into a new 32-bit number, so you have an overflow error. Or you can have an underflow error, or you can have a divide by zero error. And we could say these are all versions of mathematical errors. So what we can do is we can write code, and then if a mathematical error occurs, here's what you should do. But we can be more specific, and we can say if a divide by zero happens, do this instead. So we could write code. The way we write our code, and this is, almost every programming language allows for software interrupts or software exceptions, is if you have some code that you believe there's a reasonable probability will have an exception occur, or an interrupt, software interrupt. You can say, and this is true in C++ and Java and many languages, C#, you can say try and say open paren and close paren. And what you're basically saying by saying try is you're saying I acknowledge this may not work. So let's give this a try, right? So you're saying let's try this. And from here to here, if an issue should occur like an overflow error or a general math error or a divide by zero error, then so if an overflow happens, write in if some line runs that says A plus B equals C, and A and B are it's a 32-bit machine, and you have two 32-bit numbers added together gives a 33-bit number. You can't store it, so then we could write code what to do here. Maybe we can put in 32 bits of all ones, that's the biggest number possible, and maybe you don't mind that won't hurt your computation. So what we're doing is we're saying while this code is running, that's in the try block, while this code is running, put these three possible errors on top of the stack of all the possible errors that could occur. So the reason we want to stack them up is it allows you to put priority, handle this one's more important than this one, or this one's more specific than this is a more general case. So what you can do is if an error occurs, we go looking down the stack, from the top of the stack down to the bottom until we hit the error that just happened with the error handlers on our stack. And as soon as you get the first hit, that's the error handler that we run. So we don't have to have the address of the code, you actually write the code right in here. And most programming languages have so in other words, when you're putting entries on the stack, you use the word catch. And the origin of the word catch is whatever the error that comes up, like when we were talking about hardware errors, we had a number, like number 4, we said was the internet's not connected. So that would be the error. What we end up doing here is we take a piece of storage and we fill it in with data about the error and we send it to this stack. So it's kind of like the program that generated it is throwing it to the stack, and the stack has to catch it. So that's the origin of the word catch. So we just go popping down the stack until we find the error that matches the error that we are prepared to handle, the one that matches the error that happened to have just occurred. So once those go, yep, okay. So once those go, that ends up being the way it's handled. So software is slower than doing it in hardware. When we talked about hardware, we said that as soon as the piece of hardware that has a problem knows what its problem is, it immediately puts its number in the interrupt register, which then turns wires on that says, okay, here's the address of the first line of code that handles that issue. So I guess one side thing would be, what happens if 2 errors happen at the same time? Suppose the print, the internet disconnects and the printer's out of paper right at the same time. So the internet disconnecting writes a 4 here, and then we're in we have some code. We have the first line of the code that handles that problem. Then all of a sudden another problem occurs. The number gets written in the same register, and then a new interrupt handler starts running in the middle of the old interrupt handlers running. So you have any suggestions on?
I mean, I'm sure the computer processor would probably just respond to the most immediate problem first. And either way, even if you fix the first problem, it'll still have the second problem, so the code would still run through, even if it had to go through the system.
Yeah, so I mean, there's probably a few things. One thing, what, we used to have 60, you know, so we could dedicate one bit, instead of a number, like 0001 is one, you know, printed out of paper, 0010 is processor is overheating. Maybe we could dedicate one bit to each problem, and then let each problem turn on their bit. So now we could have a bunch of bits turning on, you know, so maybe turn a bit on here, and then maybe a second bit on. So all the bits that are ones indicate a separate problem. But then we still run into the issue of, you know, how do we sequentially let one error handler run, then let the next one run, and so. We could also, another solution would be to have, you know, 2 interrupt registers. So if the first one if they're both zeros and you have a problem, you write it to the first one. And if the first one is on, if this wire is on, you write your problem to the second one. There's 3 in a, you know, 3 different problems at the same time.
At that point, you throw out the print.
Yeah. That's kind of like, you know, on an airlines, we have 2 pilots in case one has a heart attack. You know, what if they both have a heart attack? So yeah, so hopefully that would never happen. So there's a couple of ways around it, you know, handling multiple problems at the same time and having the code run efficiently. But so yeah, so just as a, you know, as a recap, interrupts are events that occur during the normal processing of your program that cause the program to not be able to run. I don't want to say not be able to finish, because it sometimes can finish. Not be able to run normally. And the interrupt problem has to be addressed. It could be addressed in such a way that it gets addressed and then your program goes back and finishes, or maybe not. Hardware versions are whenever there's mechanical problems with hardware components of the computer. And then software versions, which they tend to call exceptions more often than interrupts, can be handled easier. So if an issue comes, it just gets reported to the processor, and the processor can then handle it however it wants. And there's a lot more flexibility, so you can write code that uses exception handling. So you say, I have this code, I anticipate it may have problems, and if it has these problems, handle them in this way. If you don't have the problem, then the code doesn't run.